In this video, you're going to learn how to integrate machine learning into a control system using Tensorflow and MQTT. In the first section, I introduce you to the control system behind our demo factory, which I built in order to bring context and to demonstrate a real-world application of machine learning as opposed to just showing graphs and numbers. Then in the second section, I show you how to put together an MQTT publish-subscribe communication network that will serve as an interface between our control system and a machine learning solution. And then in the last section, I first give you a brief explanation of convolutional neural networks and introduce you to the tools used for machine learning development. I then take a deep dive into showing you how to gather images and use TensorFlow to train an image classification model, test it, and convert it into a Lite version for it to be deployable on tiny devices such as the Raspberry Pi or any other industrial IoT gateway. I then go on to deploy the model, build an image classification solution using Python, and then integrate the machine learning solution with our control system using MQTT. My name is Kutsai Teresa with Industry40.tv, and I regularly publish Industry 4.0 and Industrial Internet of Things videos on this channel. So if you're new here, don't forget to subscribe and click on the notification bell to make sure that you never miss any of the videos. I've put together a demo factory resembling a real production line with real PLCs and real sensors. However, the assumption here is that you either have a basic familiarity with control systems or you are an experienced control systems engineer. So this is not a PLC programming or control systems design tutorial. Rather, it is an exploration of how I have put together this control system so that you will be able to follow along as we bring in different layers of technology into the system. The main aim of this section is to focus less on the implementation details, but at the same time giving you enough information to appreciate what is going on and be able to apply it in your own environment. And in order to demonstrate how machine learning can be integrated into an existing factory, we're going to give our factory the ability to use computer vision to accurately identify a product on the conveyor belt and sort it appropriately. So we've got a production line that consists of two conveyor belts. Our first conveyor system is the entry point of a product on its way to packaging. And on this conveyor, we've got a proximity sensor to detect the presence of a product on the conveyor belt. So when a product is detected, the conveyor is stopped so that the product can be correctly identified using an HD camera connected to a Raspberry Pi. This is where we're going to apply machine learning image classification in a later section. So after product identification, the product is released on to the next conveyor system, which has a sorting mechanism. And then to control everything, we have our control unit here that is centered around an Opto22 programmable automation controller. So already here we can see that we have two layers of technology: our control system that uses traditional operations technology and a machine learning application that uses information technology concepts. So at some point we have to find a way of passing messages between the two. So this is our production line. It consists of two conveyor belts, the main conveyor and the small conveyor. On the main conveyor belt, I've got a proximity switch to detect the presence of a product. It is normally high and produces a low voltage on product detection. So this serves as a signal for the controller to stop the conveyor belt for product inspection. And then here, I've got a high definition camera connected to a Raspberry Pi 4B+. So upon product detection, control is passed onto this computer vision system to identify a product and send information to main control for appropriate product sorting. The main focus here is on the use of TensorFlow machine learning framework for industrial applications. So the choice of hardware here is merely for convenience purposes. You could use any Linux-based system with an HD camera. And then here The main conveyor is being driven by this stepper motor at a constant speed. The small conveyor is also driven by a stepper motor which I have set to operate at 2 speeds, high and low. And then finally here at the end of our production line we have a sorting system. And then finally here at the end of our production line we have a sorting system. So based on the results of our computer vision system that are passed to the main control system, the sorter positions itself to push product either into product bin to its left or the product bin to its right. So the sorter can only assume 2 positions, left and right. The sorter also uses a stepper motor to move back and forth as it sorts products. Now here we've got our main control system unit. I'm using an Opto22 programmable automation controller as the main control device. And then I've got the controller's I/O modules on this rack. And also we'll identify the possibilities of integrating the edge intelligence layer onto our control system. So what you are looking at right now is PEC Control Professional, a software for programming Opto22 programmable automation controllers. This is a flowchart based programming environment, so I believe it is going to be very easy for you to follow along. Let's start by looking at the run main conveyor chart. So this chart basically performs a routine for running the bipolar stepper motor driving our main conveyor belt. So as you can see, this chart continuously runs on 2 conditions. A, if the software flag is enabled, which by default is, and B, if the conveyor is not stopped manually by pressing the run main conveyor input switch. Next, we go to our run small conveyor chart. This chart runs our small conveyor belt and it operates exactly the same as the main conveyor chart. Let's move on to our control process chart. Now this is the chart that performs the main control logic for our production line. Here we start by reading the proximity sensor to check if a product has been detected on the main conveyor belt. If there is no product detected, we make sure to keep the product lights off and keep checking. Once a product is detected, we stop the conveyor, and then this is where in later sections of the course I'm going to show you how to use MQTT to trigger our Tensorflow image classifier to identify the type of product and return the result to the control system. We'll check the result and then proceed with the process. So once we've received the type of product detected, we check what it is and then we switch the corresponding LED light. And then before we restart the main conveyor, we check to see if the sorter is currently engaged. If it is, we loop until it becomes disengaged. When the sorter is free, we first check what position it is currently on, and then based on the type of product to be sorted, we move it to the correct position. And then after that, we tell the sorter what type of product it is, and then we start the chart for sorting and re-enable the main conveyor belt. And then finally, we make sure that the product clears the proximity sensor before we start checking for a signal. And then we go through the cycle again. Now let's take a look at the run sorter chart. So here in our run sorter chart, the first thing that we do is to lock the sorter to make sure that no product is sent to the sorting platform while it is busy sorting. We then check what type of product is to be sorted, and then we wait until the product reaches the sorting blade. When it does, we move the blade either to the right or left depending on the type of product to be sorted. And then after that, we create a product object consisting of the product details and store it in the controller's onboard persistent memory. And then this point is also another opportunity to transmit the product object for storage in an external system. After storing the product details and transmitting them, we set the current position of the sorter. Now let's take a quick look at the charts for moving the sorter left and right. Now these charts basically move the stepper motor a predefined number of steps to the right or to the left to reach the desired position and hence achieve sorting. I'm going to show you a quick demonstration of our control system in action. So we're going to run it without the Raspberry Pi image classifier module, as at this stage we only want to demonstrate that our control system performs as intended, which is run conveyors, detect the presence of a product, stop conveyor, adjust sorter, and sort the product. So let's see what that looks like. So our products are classified as integers 0 and 1, so this should default to 0. Welcome back. So at this stage, I believe that we are on the same page as to what kind of control system our demo factory is composed of. Now, what we want to achieve is to be able to bring in a machine learning application, specifically a Tensorflow image classifier, to classify products on our conveyor belt using a camera and then send the commands to our control system. And we have identified in our control logic the section where we would want to make decisions in our control systems based on the computations that happen on the machine learning application. Now, because our machine learning application and our control system do not share the same communication protocol, we need to find a way to pass commands back and forth between the two systems. And for our approach in solving this problem to be meaningful, it has to work with almost any control system. So in the next section, I'm going to introduce you to MQTT, a publish-subscribe form of communication that would allow us to achieve that kind of seamless interaction between our two systems. So for you to really appreciate this form of communication, let's first look at the traditional industrial communication methods. So typically, you'd have your control applications running on devices and machines connected together on a controls network. And then you'd have higher level applications such as HMIs connected directly to these devices and machines. In most cases, the type of communication that is used between these devices and applications, and sometimes between devices themselves, is a point-to-point protocol. What this means is that there is always a client and a server communicating directly with each other. A client sends a request and the server responds. What's worse is that this client-server architecture is in most cases implemented using proprietary application interfaces only known to and provided by device vendors. Unfortunately, this means that applications become dependent on a particular device they control. You cannot remove a device and replace it with one from a different vendor, not without providing protocol implementation details. And of course, you cannot access the device data using some cloud-based analytics software that has no knowledge of industrial communication protocols. Such a communication architecture is said to be tightly coupled. Now, on the other hand, the publish-subscribe pattern provides an alternative to traditional client-server architecture, which is the participants of the network never contact each other directly. In fact, they do not even need to be aware of each other's existence. The connection between them is handled by a third party called the broker. Both participants, which could be a PLC and an HMI, are called clients, and they have the capability to send and receive messages through the broker. When a client is sending a message, it is called the publisher, and when it receives the message, it is called the subscriber. The job of the broker is to filter all incoming messages and distribute them correctly to subscribers. In a nutshell, there are two key elements that this pattern embodies. A. The publisher and subscriber do not need to know each other's location in terms of IP addresses and port numbers. B. The publisher and subscriber do not need to run at the same time. If the subscriber is offline, it will receive the messages when it reconnects. All direct communication totally removed, and thus making it easy to merge control systems with IT systems without them knowing about each other's implementation details. For example, merging our operations technology-based demo factory control system with our IT-based image classifier, as you will see later in this course. I'm going to show you how the MQTT publish-subscribe communication protocol works. So, when a publisher sends a message to the broker, it provides a subject, which is called a topic. And then every subscriber interested in receiving the message from this publisher has to know the name of the topic, and then go on to use it to subscribe to the broker for that information. And from there, the broker ensures that receiving clients get all messages published to the subscribed topics. Topics are strings that look like the following examples: demo factory / main conveyor / motor speed, demo factory / temperature, or simply temperature. Notice how a slash is used to introduce hierarchy. Now, there are many protocols that implement this pub-sub architecture, including MQTT and AMQP. However, in this course, we are going to be dealing with MQTT. MQTT has another interesting feature that could be of use in industrial communication. It allows the publisher and subscriber to specify what is called the quality of service, or QoS. There are levels to QoS. There is level 0, which you can use if you don't mind losing a few messages occasionally. For example, if you are sending telemetry data after every few seconds or so. And then there is level 1, which guarantees that your message arrives at least once, meaning you should be fine even when there is multiple deliveries of the message. And finally, there is level 2, which is used when it is very crucial that your application receives the message exactly once. QoS level 2 would be a perfect fit for using with our image classifier to send control signals to our control system after identifying the product, because we don't want any messages getting lost and we don't want any duplicate messages. So, in essence, we have two participants on this network: the Opto22 industrial control device and the Raspberry Pi running our Tensorflow image classifier algorithm. So, when our conveyor stops for product inspection, we want to send a signal to the Raspberry Pi to trigger the image classifier to identify the product and return the result to the Opto22 device. So, first of all, we are going to introduce an MQTT broker. There are many MQTT broker implementations to choose from. Most of them are open source and free to use. For example, Mosquito, RabbitMQ, etc. And some, like HiveMQ, have free open source and enterprise editions. In this course, we're going to use HiveMQ for no specific reason other than the fact that I'm well acquainted with the software. But as a general rule of thumb, I would suggest you use the free and open source tools for prototyping and then use the enterprise editions for production environments, because then it comes with full support. Now, our MQTT broker is going to be deployed on a Windows PC. Again, the choice of the hardware is entirely up to you. You could use a big Linux or Windows server, a PC, or some industrial IoT gateway. The point is to have the device located at the edge, which is your factory floor. So we're going to have two topics in our MQTT architecture. The first topic is going to be demo factory / ready to detect. This is the topic to which the Opto22 device publishes a message when a product is detected in order to let the image classifier know when to start identifying the product. The image classifier will subscribe to the same topic in order to receive the message. The second topic is the demo factory/product identity. This is the topic to which the image classifier publishes a message after completing product identification in order to let the control system know the identity of the product and proceed with production. The quality of service for both topics will be set to 2 so that the Raspberry Pi and the Opto22 device all get the messages exactly once. The Opto22 device MQTT client capabilities will be implemented using Node-RED, and the image classifier MQTT client capabilities will be implemented using Python. I'm going to show you how to deploy an MQTT broker on a Windows PC, and we're going to be using the Hive MQ broker, which can also run on Linux and Mac OS devices. Now, as of recording of this video, Hive MQ requires Java version 11, and that might be different in the future. So, in order to download the Hive MQ broker software, you must go to the Hive MQ website, which is hivemq.com, and then you click on the Get Hive MQ button, which takes you to their downloads page. Now here they have download options which include a zip archive, Docker, and an AWS installation. We're going to choose the zip archive. And after that, you can fill in the form and click submit to proceed with the download. So I've already downloaded the zipped file and extracted it onto my C drive. Now, to run the MQTT broker, you open your extracted folder, and then you go to the bin folder, and then here you right click and run as administrator the run.bat file. And then after a couple of seconds, your broker will be up and running. Now, if you need to access the control center of your MQTT broker, you can do so by going to your browser and typing in localhost at port 8080, which is the default port, but it can be changed. And then you can enter the default username and password, which is admin, and Hive MQ for your password. And then you'll get your control center dashboard. Your MQTT broker can be accessed at port 1883 for non-secure communications and at port 8883 for SSL connections. So now that our broker is up and running, we can go ahead and create MQTT clients and test if it is working. I'm going to show you how to make our Opto22 device a client to our MQTT broker using Node-RED. Now, I have to mention that Node-RED is not the only solution that can give your control system MQTT client capabilities. Some PLCs are MQTT enabled by default, or you can use a C# or Java MQTT client running on a PC and communicating to your PLC. Or you can also use a gateway device that talks MQTT on one end and communicates to your control system on the other end. Now, with that said, first of all, let us go back to our control logic so I can show you how I have implemented the triggering of the image classifier and the reading of the product identity. So here I'm on my main control chart that we discussed earlier. Now here on this block, I have added a code that sets the value of an integer variable called trigger image classifier to a value of 1 in order to enable the triggering, and then I set it back to 0 after 500 milliseconds. When that happens, our Node-RED MQTT client will detect that integer value of 1, and then it will publish a value of 1 to the MQTT topic called demofactory/ready to detect. And then after that, our control logic will loop until it receives the product identity from our image classifier via MQTT. When the Node-RED client receives the product identity, it will write it to an integer value called product type holder, and then it will set a flag called product identity received in order to notify the control system to read the product type. Okay, so let's take a look at how our Node-RED MQTT client works. So as you will see, here I'm mainly using an Opto22 Node-RED package which I installed on the platform to read data from my PLC. And for variation, I'm using a Modbus package which I also installed to write back the product identity and set the data ready flag. I'm also using MQTT publish and subscribe nodes which come pre-installed with Node-RED. Now here I'm on my Node-RED editor running on my PC. This flow that you're looking at right now is divided into two parts. The top part here is responsible for publishing to the topic demofactory/ready to detect. So here I'm continuously polling the trigger image classifier integer variable. When its value changes to 1, I publish a value of 1 to the demofactory/ready to detect topic to trigger our image classifier. And then this bottom part here is subscribed to the demofactory/product identity topic. So when our image classifier has finished product identification, it will publish the identity to that topic and our client will receive it. And then our client will write the value to the product type holder tag, and it will also set the product type received flag to notify the control system. Now, if you check on both our MQTT publish and subscribe nodes, you will notice that we have got our MQTT broker details specified. So as you can see here, it is running locally on port number 1883. I'm going to show you a real demonstration of our demo factory control system publishing and receiving MQTT messages, which it then uses to make control decisions. Now, in place of the image classifier MQTT client, which we are going to build in the following section, I will use an MQTT client software called mqtt.fx for testing. So I'll open the software, and the first thing that we need to do is to configure its MQTT broker details. Now to do that, I'll go to the settings, and then here on broker address, I'll put localhost, and then I'll leave the port at 1883. Then I'll click apply and OK. And then from here, I'll go ahead and connect. If my connection to the broker is successful, this indicator here will turn green. Okay, so I've successfully connected to my MQTT broker. Now, the next thing that we need to do is to subscribe to the demo factory/ready to detect topic. So I'll click on the subscribe button, and then I'll type in the topic name, and then I'll click on subscribe. So now our image classifier MQTT client is waiting for the ready to detect signal. Okay, so we've got our demo factory here, and I'm using this Lego brick as my product. So I'll start the conveyors. Now, if our system works, we should get a ready to detect MQTT signal on our MQTT.fx client as soon as the proximity sensor detects the product and stops the conveyor. Okay, the conveyor stopped, and there instantly we get our ready to detect MQTT signal. Now, before we proceed, I'm going to turn the camera to face the LED indicators so that we can have a visual depiction of our result. Now, our control system is awaiting a product identity MQTT signal. So we're going to publish to that topic. Now I'm going to publish an identity signal of the value of 1, which corresponds to our red LED. Now as soon as I hit the publish button, the red LED should come on and our production line should continue running. So there you can see we've got our red LED on. So in this section, we managed to implement a publish-subscribe communication pattern using MQTT for our demo factory. What this has allowed us to do is to remove a barrier that normally exists between industrial control systems and IT applications. Therefore, we are now able to bring in different layers of technology to augment our operations at the factory floor. More importantly, our MQTT implementation is at the edge of the network, closer to our devices and machines, allowing us to make use of industrial IoT communication without the latency of using a cloud-based server. So overall, we are now able to build our Tensorflow image classifier and integrate it with our control system using our new PubSub communication architecture. In this section, I'm going to take you through a detailed workflow that is required in order to successfully implement a machine learning application at the factory floor. And in order to give you a deep understanding of the potential applications of machine learning at the factory floor, I'm going to build and demonstrate a machine learning application using a real-world scenario. We're going to make our demo factory an apple sorting factory. And we will be sorting between two types of apples, red and golden. So in order to accomplish this task, we're going to perform a series of tasks that involve the following: acquiring a dataset of images of red and golden apples, using the dataset and TensorFlow framework to train a machine learning model to predict what category or class an apple on a conveyor falls into between red and golden, deploying that model to a device in our demo factory, building a Python application that utilizes the model to send MQTT commands and control signals to our control system based on the results of the image classifier. My main goal is to introduce you to the key machine learning tools and techniques such that by the end of this section, you will be able to build your own machine learning applications from start to finish. Now, because of significant development in the field of AI and machine learning, much of the mathematics involved has been abstracted and packaged into frameworks that allow non-mathematicians like myself to easily apply the technology in our respective fields. Examples of such frameworks include TensorFlow from Google and PyTorch from Facebook. In this course, we're going to use TensorFlow. In this video, I'm going to give you a brief introduction to convolutional neural networks, and I'll also introduce you to the idea of TensorFlow. So, convolutional neural networks, called CNNs, are a deep learning technique that is responsible for most of the advances in computer vision today. There are two main components involved in CNNs, which is convolution and max pooling. So let's take, for example, a grayscale image of our apple. This image consists of pixels, each represented by a number that ranges from 0 to 255, with 0 representing black and 255 representing white. So the apple images in our dataset are 100 by 100 pixels, which means our image can be represented by a 100 by 100 matrix. So if we want to add a convolution layer, we do so by creating a filter, which could be a 3 by 3 matrix, and then we use that filter to scan through each pixel in our image, multiplying its nearest neighbors by the corresponding pixels in our filter, and adding the result to come up with a new pixel value. After we've gone through all the pixels in our image, we produce what is called a convoluted image. Now, to add a max pooling layer, we take our convoluted image and then we create a max pooling matrix with a certain grid size, for example 2 by 2. And then we scan our convoluted image using our max pooling matrix, but this time not multiplying but taking the pixel with the highest value in our 2 by 2 section. So obviously this reduces the size of our image by a factor of 2, resulting in a 50 by 50 image. So after this exercise, we can conclude that we have used one convolution layer and one max pooling layer on our image. However, our image is not grayscale. It is a full color image. So what it means is that to perform convolution on a color image, you use a 3 by 3 convolution filter that is 3-dimensional, since our image has 3 color channels, RGB. Same applies to the max pooling grid size. So this is an oversimplified explanation of CNNs, as they are a much more complex topic than that. But this is so that you don't get confused when we select the number of convolution and max pooling layers later when we train our model. I do, however, advise that you read up on convolutional neural networks in order to have a deep understanding that will make you good at training computer vision models. But lucky for us, we don't have to go that deep to implement our apple sorting factory using these deep learning techniques. We've got Tensorflow, a free and open source machine learning toolkit that enables us to build and deploy machine learning applications. It consists of software packages and libraries which simplify the machine learning programming experience. And then we've also got Keras, an even higher level neural networks library which runs on top of TensorFlow framework. It allows us to rapidly build and train deep learning models using convolutional neural networks. In fact, you can actually train your CNNs in about 10 lines of code. In this video, I'm going to introduce you to Google Colab, a cloud-based platform that gives us free access to state-of-the-art computing resources for training our machine learning model. So machine learning has been out of the reach of many people due to the fact that training machine learning models is a very computationally intensive task. Hence the reason why we have seen an explosion of ETH usage since the advent of cloud computing platforms that make it relatively cheap to rent a powerful computer. Now, the challenge that exists today is that setting up the cloud infrastructure is still a time-consuming and sometimes frustrating process. That is, provisioning the servers, installing the frameworks, and resolving any incompatibilities that might arise. What we generally want is a platform that lets us start prototyping right away without worrying about the underlying infrastructure. Google Colab is such a platform. It runs in the cloud and requires no setup, and it provides you with a simple interface that allows you to quickly build and test your machine learning models and even share the code with anyone. This is the platform that we're going to be using to build and test our models in this course. To access Google Colab, you go to colab.research.google.com and use your Google account to sign up. In this video, I'm going to show you how I have gathered the Apple images and organized them into a training and validation dataset. So the first thing that I did is that I went on the internet and looked for image datasets of apples. And I found this GitHub repo by Horia Morrison. It has got a variety of fruits, including red and golden apples, which makes it useful in our case. So what I then did is that I downloaded the files and saved the red and golden apple images on my C drive. The directory structure that I created is as follows. I called the main directory red and golden apples with underscores. Inside that directory, I created two directories, train and validation. The train directory holds images that are going to be used to train our model, and the validation directory holds the images that are going to be used to test our model. After that, I split my red and golden images into 80-20 ratio. That is, I took 80% of red apple images and put them in a directory called red inside my train directory. So these are the red apple images that we're going to use to train our model. And then after that, I put the remaining 20% in a directory called red inside my validation directory. And these are the red apple images that we're going to use to test our model. And then I did the same for golden apple images. So these are the golden apple images that we're going to use to train our model. And lastly, these are the golden apple images that we're going to use to test our model. So the reason why we split our images into the 80-20 ratio is so that we can have a certain set of images that our model hasn't seen, so that we can be able to determine its power of prediction. And then from there, I compressed the red and golden apples folder into a zip file and uploaded it to my Google Drive. In this video, I'm going to show you how to use Tensorflow and Keras API to train our image classification model for classifying red and golden apples. So we're going to be using the Python programming language for this exercise. So here I'm on my Google Colab platform and I've just opened the Python notebook that contains my code. Okay, so the first thing that I'm going to do is to install Tensorflow GPU version 2.0, and then I'll also install TensorFlow Hub, which allows us to import some reusable code. I'll execute. Now our environment requires that we restart the runtime after installing TensorFlow, so I'll go ahead and do that. And then I'll go on to install the required packages. Key to notice here are the Keras image data generator, which allows us to read our image dataset, save it onto local disk, and generate training and validation data. Keras image data generator also allows us to perform image augmentation, as you will see later on. The second one is the OS package, which allows Python to read files and directory structure. And then we've got NumPy for some math, and matplotlib.pylot for plotting graphs and displaying images. The logger package is for logging messages, and finally we've got pandas for data presentation. Next, we print out versions for TensorFlow and check if GPU is available. So using a GPU instead of a CPU is a much faster way to perform training. And to switch between the two, you go to Runtime here and select Change Runtime. And then you can select your hardware accelerator here. So I'll go ahead and execute this. Okay, now let's use Keras to get our dataset where I uploaded it on my Google Drive. and then we print out the directory structure of our zipped folder. So here you can see that we've got our red and golden apples directory, and inside that we've got validation and train, and inside those two we've got red and golden. Okay, and then now we need to create the variables that will hold the path to our training and validation pictures. And then here we read the number of images in each directory, we calculate the totals, and then we print out the details. So as you can see here, we have a total of 372 images each for red and golden apple training images, and 100 validation images each, giving us a total of 744 training images and 200 validation images, which is almost 80 to 20%. And then we set the batch size, which is the number of training images to process before updating our model's variables, and the image shape, which is the pixel size of our training and validation images, which is 100 by 100 pixels in our case. Now we need to generate the training data from our images. So we use image data generator. First of all, we apply image augmentation, which means we apply image transformations to our dataset, such as zoom, flip, shift, and rotate, etc. This is so that we can give our model different angles of images to improve its prediction capabilities. And then we generate our training data and put it into train data gen. Then we click on execute. And then we use data generator again to generate our validation data and put it into val data gen. Okay, and then we can print out batch information from our training data to see what it looks like. So we've got a batch of 150 images, each of 100 by 100 pixels, with 3 representing the color image channels, RGB. And then let's extract the labels from our dataset. And we've got golden and red as expected. To verify that the dataset looks correct, let's plot the first 5 images from the training set. And then we plot. So these are our images, and they are all 100 by 100 pixels, so everything looks correct. Okay, now we create our model using the Keras API by stacking convolutional layers that use 3 by 3 matrix filters and pooling layers that use 2 by 2 matrices. And then we're going to activate what is called a ReLU, which is a mathematical function that gives our dense layer more power. Our model will give us an output of probabilities for red and golden apple classes, And to enable our model to provide probabilities for each output class, we're going to activate a function called softmax for our model output. So I'll execute our model creation statement. And then next, we compile the model. So as you can see, our compile method has 3 arguments. For the first one, we used Adam. This is an algorithm called adaptive with momentum. Its job is to recalculate and update model variables after every batch. The second one, sparse categorical cross entropy, is a loss function. Its job is to evaluate how good your model is at predicting the output. And then finally, we would like to look at the training and validation accuracy. So I'll execute the statement to compile our model. Let's display the architecture of our model so far. Here you can see that the output of every convolutional and max pooling layer is a 3D tensor of shape, height, width, and RGB channels. Finally, let us train the model. So here I set it to 10 epochs. So epochs is the number of iterations that I want to perform. So I'll go ahead and execute. Okay, so our model training is complete. Let's display our model accuracy. Okay, so as you can see, our model gained 100% accuracy after the first few iterations and then just stayed there. So the danger here is that this could result in overfitting, whereby your model is simply memorizing the data, which could compromise its prediction capabilities. It's not very usual to get 100% accuracy. So another reason here in our case could be that we really have a very tiny dataset to train our model. There are many ways to prevent overfitting, but for our demonstration here, this will suffice because the point is to show you how to train this and then how to make a prediction out of it. In this video, I'm going to show you how to save our TensorFlow model created in the previous video. We're then going to load it back and test its performance. So continuing from where we left off, so we want to save our model with a timestamp. So we're going to import time and then specify the path where we wish to save our model. And then we're going to use TensorFlow saved model to save the model. So a model can be saved using different formats, and the format that we're using here is called the saved model format. So I'll go ahead and execute this statement. Okay, so our model has been successfully created. If you check under files here, you should see your model. If you don't see it, you just need to refresh. Okay, now we're going to load our model back for testing. We're going to call it Apple's model and specify the load path using TensorFlow Hub. So I'll go ahead and execute the statement for loading the model. Now let's check what our validation images batch looks like. We'll read that from the val data gen into val image batch and val label batch variables. So I'll go ahead and execute that. So as you can see, we've got a batch of 150 validation images with 100 by 100 pixel size and 3 color channels. So that looks okay. Now let's look at what predictions we get for our validation images batch. So we do that by passing the validation batch images to our loaded model. So I'll go ahead and execute the statement. So we have a prediction of 150 images with a 2-class output, which is red and golden. Now let us use pandas to visualize what our first few predictions look like. So I'll execute that. So as you can see, for our first prediction, we got a 0.99 for the golden apple, and we got a 0.00 for the red apple. And for the second prediction, we got a probability of 1 for the red apple and a very small number for the golden apple, and so on and so forth. So our predictions look okay. Okay, now let's get image labels from our predictions. So I'll execute the statement for getting the labels. And then let's plot them against our image predictions to see if our predictions are correct. So I'll execute that. Okay, so as you can see, our model has correctly predicted all the images that we're looking at. Red apples are labeled as red and golden apples are labeled as golden. In this video, I'm going to introduce you to Tensorflow Lite. Now, earlier on in this section, I mentioned that performing machine learning requires a lot of computing resources. And this is the reason why most machine learning tasks are performed using powerful machines in the cloud. However, there are some scenarios where using the cloud for running your machine learning applications has more disadvantages than benefits. One such example is at a manufacturing plant factory floor. Here are some of the disadvantages. 1. Latency. So whenever you are sending data back and forth from a cloud server, there's always a time delay between action and response. Meanwhile, at the factory floor, due to the mission critical nature of operations or for safety reasons, some decisions need to be made instantly. Number 2, privacy. Most manufacturing organizations are very protective of their data and operations. So having an application run entirely in an external environment is a deal breaker for them. Number 3, connectivity. Cloud computing's dependence on a stable internet connection is one of the drawbacks to adopting machine learning in the cloud. So with that said, what would be ideal is to have the machine learning application run entirely at the factory floor without the need to connect to a cloud server. This is why Tensorflow Lite was created. It allows developers to run machine learning models on embedded and IoT devices. Hence, it would be ideal to deploy on devices at the factory floor. Tensorflow Lite consists of two main components. A converter, which is used to convert and optimize TensorFlow models into a form that can be run efficiently on small devices. B, an interpreter, which is used to run these optimized models on a variety of hardware. Now let's take a look at what the conversion process looks like. So the first step is to train the model in TensorFlow, which we already have done using the Keras API. When training is done, the next step is to serve the model. And then from there, you convert your TensorFlow model into a TensorFlow Lite model. After that, you save your TensorFlow Lite model in a file with extension .tflite. And finally, you deploy your TensorFlow Lite model onto your device and run inference. Let's take a look at what the TensorFlow Lite conversion workflow looks like. So you can use three different formats to convert from a TensorFlow model to a TensorFlow Lite model. It can be from a Keras model format, a served model format, or using what are called concrete functions. And then the model is converted and flattened. And then when the model is deployed on the device, an interpreter is used to perform machine learning inference. In this video, I'm going to show you how to convert our TensorFlow model to TensorFlow Lite so that we can be able to use the model for inferencing on tiny devices with less computing power, such as the Raspberry Pi. So let's begin by creating a directory to store our TensorFlow Lite model. And then inside that directory, I'll create file path for the TensorFlow Lite model file with a .tflite extension. So you'll notice here that I'm creating two file paths, one for the quantized version of TensorFlow Lite model and another one for the non-quantized version of the model. And then here we perform the conversion by first getting the concrete function and saving it. Then using TensorFlow Lite's converter to convert our model into TensorFlow Lite from the concrete function. We then write the converted model into a .tf file whose name and path we created earlier. And then here we perform the same conversion, but this time we add the optimization option for optimizing for size. And then we write it into the quantized version of our tflite model with the .tflite extension. So I'll go ahead and execute that. So we've successfully converted our TensorFlow model into a TensorFlow Lite model. So if you check here in your files under the tflite models, you'll see two files, one for the non-quantized version and one for the quantized version. Now to test that our TensorFlow Lite models are working correctly, we must load the models back on again. We start by loading the non-quantized version. So we use an interpreter to load the model, and then we get the input and output details of our interpreter. We'll use the input details to supply images for prediction and output details to get the prediction result. Let's print out the details. So you see here our shape has got a size of 1, allowing us to make predictions for one image. But we want to make predictions for our batch size of 150. So we resize the input and output details of our interpreter to 150 images. And then when we print out, you can see that change reflected. Now let's make predictions using our validation images batch as an input. We invoke the interpreter and get output details and get predictions from the interpreter output. So I'll execute that. And then let's display the predictions using pandas. Now again, you can see our predictions for the golden and red apples. For the first prediction, we've got a 0.99 probability that it's golden, and for the red, we've got a 0.02 probability that it's red. And if you go down the list, you can see that our model is performing accurately. Now let's do the same for our TensorFlow Lite quantized model. We change the size of our data frame. And then here you can see that with our TensorFlow quantized model, our results are almost the same as for the non-quantized model. Now here, we're going to use pandas to compare predictions from our three models. And then we do a column swap for a side-by-side comparison. And then here I'm going to highlight the TensorFlow Lite model predictions that are different from the original model. So basically what we can see here is that even in cases where the predictions are different, it's usually by very small factors. Okay, and then finally, let us visualize predictions from TensorFlow Lite and quantized TensorFlow Lite models. So I'll execute this. Okay, so from what we're looking at, we can see that our TensorFlow Lite model is correctly classifying our red and golden apples. Now let's do the same for our quantized version of the TensorFlow Lite model. Now looking at the results here, we can also conclude that our quantized version of the TensorFlow Lite model is correctly classifying our images as red and golden. In this video, I'm going to show you how to deploy your TensorFlow Lite model onto a Raspberry Pi. So first of all, you want to start by downloading the TensorFlow Lite models onto your machine. So you do that by right-clicking and selecting download. Now the next thing that we need to do is to create a text file with our labels that we're going to use for annotation, so that when we display our results on the screen, we'll also display the name of the product and also the time it took to make the inference. So I'll save this text file in my downloads folder. And then when that is done, you then go on to use a file transfer software of your choice to transfer your files from your computer to the Raspberry Pi. I use a software called WinSCP, so I'll open it here. Once you've opened your file transfer software, you then move your files from your machine onto your Raspberry Pi in a folder of your choice. In this video, I'm going to show you how to build a Python application that uses a TensorFlow Lite model to perform image classification using Raspberry Pi and the Pi camera. To start building a Python application on the Raspberry Pi that uses TensorFlow Lite models to perform ML inferencing, you need to first install TensorFlow Lite interpreter. You don't need the full TensorFlow package when all you want to do is to execute your TensorFlow Lite models. To install the TensorFlow Lite interpreter, you go to the following URL, and on that web page you'll find full instructions. But to summarize it, you will find a table where you can download a .whl file. It is available for different versions of Pythons and for different system architectures. I'm using Python 3.7 on Raspberry Pi, so I would select Python 3.7 under ARM32. After downloading the .whl file, you run the following instruction on your Raspberry Pi command line. pip3 install followed by the name of your file. I've already installed that on my Pi, so you can go ahead with the download and installation. Moving on to our code. I'm using Visual Studio Code to do remote development on the Pi, meaning my Python files are located in the Pi directories. I'm just accessing and editing them remotely. However, you can use any Python development environment of your choice and transfer the files to your Pi or use the command line. Okay, so what you're looking at here is my Python script called controller.py, which is used for accessing the Pi camera and running machine learning inferences using the TensorFlow Lite model that we trained and deployed onto our Pi. So first of all, I'm importing the necessary Python packages. The most important one to pay attention to is the TensorFlow Lite runtime.interpreter. And then when you go down, this method here is the entry point into this script. I will explain later as to why it is so, as it is being invoked from an external script. So when this method is invoked, we load the TensorFlow Lite model into the interpreter using the file path of where we deployed the model on the Raspberry Pi. We also load the file that contains our labels for annotation. After we've loaded the TensorFlow Lite model and the labels, we run the interpreter.allocateTensors method. This is so that we can load our interpreter into memory in a way, and then we get the interpreter's details, which we'll use to input our image for classification. And from the input details, we get the width and height of the image size that is accepted by our model. Since our model was trained using 100 by 100 pixel sized images, it will only accept images of the same size to run inferences. And then here we call the read camera method. So if we go to our read camera method, our read camera method accepts as arguments the interpreter, labels, width, and height. So first we set the camera resolution and frame rate, and then we start the camera. We create a stream input, select to use the video port and set the format to JPEG, and then we zoom the camera and crop the view so that we can make the apple large and fit inside our 100 by 100 size. This flag is always true. I just wanted to be able to set it false for any reason. And then here we capture the image, convert it to RGB, and use our model height and width to resize the image to make sure that it will be accepted as input into our model. We start the time to keep track of how long it took to run the classification, and then we call the method that performs the classification. So if we go to the classify method, you see here that we are supplying our camera image as input into our interpreter. We then invoke the interpreter and then get the classification results from output details of the interpreter. We use NumPy to squeeze the output. So our model actually returns results that contains possibilities for both red and golden apple as an array. It will tell you what probability is that it is a red apple and what the probability is that it is a golden apple. So here we load it into an array with 1 with the highest probability at the top, which is our prediction. So here we return an array to our camera method with the highest probability at the top, which is our prediction. So if we go down to our read camera method, so here you can see the camera uses the labels to first annotate the image and then print the label ID. And that label ID is returned as the product ID to the run method. And if we go down to the run method, you can see that the product ID is returned to the calling script, which is our MQTT service in this case. In this video, I'm going to show you how to include MQTT service in our Python application in order to integrate it with our control system. Now let's open up the script called messageservice.py. So here I'm also starting by importing the necessary packages. So these include the paho.mqtt.client to make our Python application an MQTT client. And we're also importing controller, the script from our previous video that executes the image classification inferencing, as we will be invoking it from here. So if you go down here, we have a start MQTT service method which takes in broker address and port number as arguments. And then here we try to connect to our broker, and if the connection is successful, this method here called onConnect will be invoked. And inside this method, we subscribe to demo factory ready to detect topic that lets us know when to start running image classification. And then our MQTT goes into a loop that executes forever, waiting for a message to start identifying the product. If an MQTT message is received from our controller, This method here called onMessage will be invoked, and inside this method we call the controller run method from the previous video. The controller run method starts the camera and executes image classification. When the controller returns the product identity to this method first converts it to a string, and then it publishes it to the topic demo factory / product identity to which the controller is subscribed. And then finally, the entry point to our whole Python application is this script here called classify.py. So I'll open that up. So the classify.py script imports MQTT service. So when it is run with the start argument, it passes to the MQTT service the broker address, which is 192.168.0.103, the IP address of the PC on which the broker is deployed, and the port number 1883 for non-secure communication. Although in a production environment, you might want to use secure communication. And then here it starts the MQTT service. Okay, so here I've got my Hive broker running, and then I've got my MQTT.fx client to simulate our control system. So this MQTT client is already connected to my Hive MQ broker here, as you can see from the green light. So here I'll go ahead and subscribe to the product identity. Okay, our subscription is successful, and then here we'll be ready to publish a message to initiate the image classification. Okay, before I do any of that, I'll go ahead and start my Python application. And then here I'm logged into my Raspberry Pi terminal using PuTTY via SSH. So first of all, I'll cd into my project directory. And then I'll start my Python application, which is the classify.py start. Okay, so as you can see, we've got a message to say that we've successfully subscribed to the ready to detect topic. So I'm going to publish a message to that ready to detect topic to initiate image classification on our Python application. So I'll go ahead and click publish here on my MQTT.fx client. So as soon as I do that, you see our camera is running. And we've published that information of the product identity back to our MQTT.fx client. Let's see if we've received that subscribe message. And then there you see we've just received a message with our product identity. Okay, so we have successfully built up the necessary technology infrastructure to give our demo factory intelligence that is based at the edge. In this video, I'll show you our demo factory in action. Okay, so our model wasn't as perfect as it performed on the Colab environment, and there are a lot of factors that could have contributed to that, including the fact that we might have overfitted our model during training, the small number of training images that we used, and the picture quality, etc. So I really had to tune my environment here to get it to give an accurate prediction, which included not letting in too much light into the room and using red apples with less shade of gold in them. So like I said, it was far from perfect, which really is what machine learning is all about. It's not plug and play. So when an apple is detected on the conveyor, the control system will stop the conveyor and send an MQTT message to our Python image classifier application, which will then start the camera, perform inferencing, display the results on the screen, and then send the product ID back to the control system via MQTT, as we have demonstrated in the earlier videos. The control system will then sort the apples accordingly.